For this video, we will be going over how to evaluate trusses. There are a couple different methods you can use, and it's really up to personal preference on which one you're going to use when evaluating a truss. For academic purposes, your teacher is probably going to tell you which method to use, so you're going to need to know all the methods. But once you get past the academic side of it, you can really use whatever method you're most comfortable with. Also, I will show you a shortcut at the end for evaluating trusses that can make your job a lot easier and a lot simpler, and just a quick way to check to make sure that you've evaluated a truss correctly. So first we'll go over method of joints, then method of sections, and then I'll show you a shortcut. Usually, if you're in the statics class, your teacher won't let you use the shortcut because they want you to learn how to do it this way first. However, I'm going to teach you the shortcut because it is a quick way to check to make sure that you've done these correctly, because it's really easy to get going on these and make really little mistakes that you carry all the way through, and it ruins your whole evaluation. All right, so let's look at method of joints. Now, I think the best way to do this is to just start with an example and go through that. There really isn't a whole lot of before explanation that I can give you without just diving right in. So, if I just quickly draw out a truss. A, B, C, D, E. All right, so the first step we want to do is draw our free body diagram. Again, this is going to be the first thing that you do every single time. I guess we should add some loads to this truss. We'll put 10 pounds here at C, 10 pounds at B, and we'll put 10 pounds at E. All right. So again, drawing your free body diagram, you're going to start with your object, which in this case is going to be our truss. So just quickly draw that out. Oops. So we have a pin at A, so we're going to have reaction in the Y, reaction in the X. And at D, we have a roller, so we just have a reaction parallel, a reaction perpendicular to the surface. So in this case, the surface acts in the X, so we're going to have a reaction in the Y. Okay, and then we apply our forces. All right, and we also need dimensions. this as well. So we'll just say this is 5 feet and 10 feet and 10 feet. Just to make our numbers nice. So again, we'll put that on our free body diagram. 5 feet, 10 feet, 10 feet. Okay. All right, so once we have our free body diagram drawn, the next thing you always want to do is find the reactions. Now, to find the reactions, you're going to treat this truss just like you would a beam that we saw in equilibrium for a rigid body. So we're going to do our sum of moments about A equals 0. Pick a direction as positive. If you need help with this part, I would recommend you go back and you watch the video on equilibrium of a rigid body first, and then come back to this point, because finding the reactions is all a part of equilibrium of a rigid body. That's all covered in that video. So sum of moments about A, we're going to have 10 pounds times by its moment arm, which we should put those dimensions in there. Let's just say from here to here is 4 feet, and same with this side. Okay, so 10 pounds times 4 feet. And that's going to be positive, and then we've got another positive 10 pounds times 10 feet, and another 10 pounds times 20 minus 4, which is going to be 16 feet, and then minus dy times 20 feet equals 0. So we can solve for dy, and when I calculate that, I get 15 pounds going up. Now we can do our sum of forces y equals 0, choosing up to be positive. So we're going to get ay minus 10 pounds minus 10 pounds minus 10 pounds plus dy equals 0. So ay minus 30 pounds plus 15 pounds equals 0. So ay is going to equal 15 pounds going up. All right. And then if we look up here by inspection, we know that ax is going to equal 0 pounds. So we've got all of our reactions now. So the next thing we want to do is free body diagram each joint with their corresponding equations of equilibrium. And I'll go ahead and show you what that means. So for me, I always like to start at the left side of the truss and work to the right. Just be consistent so I hit every single joint and it's all okay. So for me, I'm going to start with joint A. And I'm going to go ahead and free body diagram this. So what I like to do, this is literally just the same thing as we learned in equilibrium of a particle. It is not different at all. It is exactly the same. So if you have questions about that, you can go back and watch that video. But I'll go ahead and go over it again right now. So for A, we just have this joint right here. We've got AY coming up, which we solved as 15 pounds. AX was 0, so I'll leave that alone. And then we have, I'll highlight these for you, these two truss members that are attached at A. So the way we draw that is you want to draw those forces acting away from the joint, just like that. And when we draw those away like that, we're modeling those members as being in tension. So we can, if we always model them as being in tension, if our numbers come out negative, then we know that it's in compression. And if you stay consistent, then you won't ever have to think about if it's in compression or tension. You'll know that tension is positive and compression is negative. Stay consistent and you won't get confused, I promise. So we're going to go ahead and label this force in A, B, and force in A, E. So now that we have the free body diagram of that joint done, we can evaluate this exactly the same way as we evaluated equilibrium on a particle. So for that, we just have our sum of forces X and our sum of forces Y. So by looking at this figure right here, by inspection, I can see that we have two unknowns in the X and one unknown in the Y. So for that reason, I'm going to do my sum of forces Y first, because this force will break into an X and Y. This one's just X, and this one's just Y. But this one here is known, where this X is unknown. So we know that we can solve for our Y of that. So that's why I'm starting with sum of forces Y. So we're going to have 15 pounds plus FAB Y component equals 0. So we know that the slope of this from our free body diagram up here is going to be over 4 up 5. So we can solve for the hypotenuse using Pythagorean theorem, and that's going to be the square root of 4 squared plus 5 squared, which ends up being 6.4. So now that we have the slope of that line and we figured out the hypotenuse, we can now figure out the Y component of the FAB force. So 15 pounds plus FABY is really going to be FAB times the ratio 5 over 6.4. Because 6.4 is the hypotenuse and 5 is the Y component of that triangle. And we are summing up the Y forces. And that equals 0. So we've got one equation, one unknown. We can solve for FAB, which I get to be as a negative 19.2 pounds. So as I was saying before, because this is negative, we assume tension over here, so we know FAB equals 19.2 pounds in compression. Now we can do our sum of forces X. So we're going to get FAE X component plus FAB X component equals 0. FAE is all X component, so we can go FAE plus FABX is now going to be FAB times the ratio 4, which is the horizontal part of that slope, all over 6.4, which is the hypotenuse, equals 0. Now, we know what FAB is, so FAE plus FAB is a negative 19.2 pounds because it's opposite of this picture that we drew here and wrote our equation off of, so we have to plug this in as a negative 19.2 pounds times 4 over 6.4 equals 0. So now we can solve for FAE. Which I get as 12 pounds. Positive, so we know that this is in tension. So, now that we've done that joint, we can move on to joint B. And again, you can come up and look at your Freebody diagram. You're going to draw those as tension forces. So away from the joint. However, this here is FAB, which we found up here to be in compression. So I'm going to go ahead and change the direction of this arrow because we know that it's in compression. So we're going to draw it towards the joint. It's going to be FBC and FBE. Okay. So now that we have that, you can write your equations of equilibrium and solve for your unknowns. I'm not going to do this because it's very repetitive, and I feel like once I've showed you one, it's the same process for all the other ones, so you can go ahead and do that on your own. If you do feel like you get in a jam and you're still not quite sure what the procedure is, go ahead and head over to our homework help page or our tutoring page, and we'll be able to give you further explanation there. Also, for our written examples, we go through an entire problem for you on method of joints. But we're going to go ahead and move on to method of sections. So for this, we'll just use the same truss that we evaluated in the last problem. And your first two steps for method of sections are going to be the same. You're going to draw a free body diagram, and you're going to solve for your reactions. And then once you do that, then the procedure changes a little bit. So, if you remember, A, B, C, D, E, and there are forces acting at these joints, and there were reactions. All right, so for this method, instead of evaluating each joint, you're going to evaluate a section of the truss. So let's just say, for the sake of argument, that we want to find, let's just find the same forces that we found up here so we can compare them. So FAB and FAE. So find FAB and FAE, indicate if the member is in tension or compression. All right, so because we want to find FAB and FAE, that's where we're going to cut the truss and make a section. So we are going to cut the truss with a vertical line through AB and member AE. Once you've cut it, you can look at the left side or the right side. I always like to pick the side with fewer forces. So in this case, the left side has one force versus the right side having 1, 2, 3, 4 forces. So we're going to look at the left side of the truss. And we're just going to redraw that down below. Those little squiggly line indicates that we cut through the truss at that point. And then, of course, our reaction was 15 pounds going up. So once we have that drawn, we can apply our forces from our truss members. And you want to always apply them acting away from your cut. That indicates tension. Again, if you assume everything is in tension, if your answer comes out negative, your member is in compression. Always assume tension. If you get a negative answer, it's compression. Remember that, and it'll make your life so much easier. So this here is going to be F AB and F A E. Now, when you're doing method of sections for your, when you look at this, now you have a free body diagram. Now you're going to do equations of equilibrium. Except now, instead of having a particle, you have a rigid body. So you're going to have to include moments. So we're going to go ahead and take a moment about point B. Again, if you have any questions about how to do this portion of it, this is exactly the same as equilibrium of a rigid body. You can go ahead, head over to that video, and it'll give you a more detailed explanation on what we're doing here. But I'm just going to run through this really quickly. So moment about B, we've got 15 pounds. Remember, B is up here. And that's going to be multiplied by 4 feet. That's going to be positive direction. And then we've got a negative FAE times 5 feet equals 0. So FAE equals 12 pounds. Positive, so it's in tension. Which, awesome for us. That's what we got right up here. So our answers match, so we did it correctly. So now that we've done that, we can do a sum of forces in the y direction. Or we could do another sum of moments about point E. Both of those should get you your right answer. We'll do another sum of moments just because I feel like people are more afraid of that way, but really it's not that much more complicated than taking a sum of forces. So we're going to look at this one right here. And so we've got 15 pounds times by 10 feet. And that's going to be in the positive direction. And then we're going to have an x and y component. So you have to go where this force is going to originate, which is down here at A. So our x component has 0 moment arm, so we just need to worry about our y component. And that's going to be positive FAB y times 10 feet. So 150 pound-feet plus FAB y is going to be 5 over 6.4 times 10 feet equals 0. Again, I like to keep these in brackets so I can quickly look at that and make sure I didn't forget a moment arm on anything. But we can go ahead and solve for FAB, and that's going to equal negative 19.2 pounds. Again, that negative indicating that FAB is 19.2 pounds in compression. Which, look at that, you scroll up here, and that's exactly what we got using method of joints. So we did that correctly. Now, if this problem was asking for, let's say, FEC, FED, FBC, you can cut it right here, and you would be able to find those forces. Again, you just want to cut it through whichever members you're looking for the forces of. And then just treat it like a rigid body and solve for equilibrium. So again, I'm not going to run through the whole truss, but if you want a full example, that's completed, look at our written example, and it goes through an entire problem. All right, so now I want to show you that shortcut that I talked about at the beginning, which I think is the most effective way to evaluate and analyze a truss. But again, your teachers and your professors will want you to learn those different methods, which again is beneficial to know how to do something multiple ways and understand different ways of doing things. So the first thing you want to do is just draw your truss as big as possible, and then apply your forces and reactions. Now, this trick is honestly the exact same thing as method of joints. You're just doing it to the entire truss rather than breaking down the truss and drawing each individual joint separately. You're just doing it on one thing rather than drawing out the multiple joints. So again, I like to start at the left side and work myself to the right. But you can really do whatever you want. I think when you're doing this method, it is most beneficial though to start at a reaction point. So either start at the right or start at the left. But it's totally up to you. Again, I like to just stay consistent with how I think through things so I don't get confused or get messed up halfway through. I forget what I'm doing or get confused at what I've done so far. If I just stay consistent, it makes it a lot easier for me. So I'm going to start right here at A, and I'm just going to look at this corner right here. So I know that we have 15 pounds acting up. So I know that I'm going to need 15 pounds acting down to counteract that. So I'm going to go ahead and draw an arrow down, and I know that I'm going to need 15 in that vertical direction to counteract that 15 pounds acting up and cause it to go into equilibrium. So once I have that, I can use similar triangles to figure out this right here. So I know that the slope of this line right here had a triangle associated with it that looked like this. And we figured that out from above. So I know that that triangle is going to be similar to this triangle. So I can go ahead and set up a ratio here. So I'm going to do 5 over 4 is equal to 15 over x. And you can solve for x. And x is going to equal 12. So now I can use Pythagorean theorem and find the force acting in member AB. So again, that's just the square root of the sum of the squares. So the square root of 12 squared plus 15 squared equals 19.2. Now, because this arrow is going down, these arrows need to be going in opposite directions acting on this member. So I know that it goes like that. Now, when we're doing this method, arrows that act away from each other, like these, indicates compression. Now, if you end up with arrows that are acting like that, that indicates tension. So this is a little counterintuitive to what you would think. But just remember that it's opposite of what's intuitive, and you'll be okay. So away from each other, compression, towards each other, tension. So for force in AB, we have 19.2 pounds in compression, which we can go up here, and that's exactly what we got here. So great, we checked ourselves, awesome. So now we can again come down, look at A. Now that we have this arrow in place, we can see that there's 12 pounds going to the left. So to equalize that and create equilibrium, we need 12 pounds going to the right. So we know that the force in AE is going to be 12 pounds. The arrows are acting towards each other, so 12 pounds in tension. And we come up here, and that's exactly what we got using our other methods. So we did that correctly. And again, you just continue to work yourself around the truss, and you'll be able to figure out the rest of the forces. Again, this is where I'm going to stop at this point working on this problem. If you feel like you are having trouble grasping this concept, go ahead and shoot me an email. And I'll put up another video with a full problem of that done, because this took a little bit longer for me to grasp when I was learning it, but I feel like you've got enough information to at least get you started. But if you are still struggling, shoot me an email and I'll put up another video if we need one. If you ever have questions, comments, concerns, feel free to email me anytime, or you can also use the chat function that's found at the bottom of this webpage. Also, check out our tutoring page and our homework help page for additional resources.